Welcome back, everyone. As usual, we have a few minutes before the official class start time. So if anybody has any quick questions for me, you can ask them now. Yes, the cat is doing fine. In fact, she's currently sleeping behind the monitor on my desktop right now. I'm sure she appreciates the concern. So the question is, what questions of A4 should we be able to answer? I think most of them, and certainly by the end of Wednesday's class, all of them. So don't be afraid to start working on A4. So if you see a question on A4 that you don't know how to approach, it's not because you haven't learned the necessary material yet. It's because you haven't seen the connection to the appropriate material. Okay, so let's remember where we left off last class. So we had been studying expected value, and in particular how to compute expected values using indicator random variables, as well as linearity of expectation. And sort of the last example we saw was this simple algorithm here for computing the maximum in an array of n numbers that just basically starts by setting the maximum to be minus infinity and then looping through the array, and each time you see a value which is bigger than the current maximum, you update the current maximum. At the end of this process, this variable m is equal to the largest value in the array, and so you return m. Okay? This is very straightforward code. It's the kind of thing you might get in a first-year programming assignment, the first time someone taught you about looping over arrays. And the only sort of question about it is this line 4, where you update the maximum value. How many times does that execute? We saw that maybe it executes only once in the case where the maximum value is actually stored in A1. It might execute n times in case the array is sorted in increasing order. Then each time you go through, the next value you see is larger than everything else you've seen, so you get updated every time. And if the array is a random permutation of n distinct values, then the number of times this line 4 executes is this number hn. It's called the nth harmonic number. And it's just defined as 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on, all the way up to 1 over n. And we saw that this nth harmonic number, that's it here, same thing as this, it's sandwiched between the natural logarithm of n and the natural logarithm of n plus 1. So it's almost, when you see the nth harmonic number, unless you care about that extra constant, basically it's like the natural logarithm of n. Okay, so that's the thing to remember. And from this formula, you can kind of read off the proof. So it used indicator random variables, which is, we define an indicator random variable called I sub I, or maybe it was x sub I, that is equal to 1 if this line executes during the ith iteration and 0 otherwise. And we saw that the expected value of x1 is 1, right? The first time through this loop, we always execute this line because m is minus infinity, so that the first time through this definitely executes. The second time through, it's the probability that we execute this line is 1/2. The third time through, it's 1/3, and so on. So that's how you get that result. So today we'll look at another example where these harmonic numbers come up, another couple of related examples. And if you've been taking COMP2804, this will kind of complete the picture of some of the things we've done there, or if you've taken it in the past. So we'll look at this algorithm, Quicksort. And here is, it's not even pseudocode, it's almost complete Python code. There's just a def and a colon missing here at the beginning to make this valid Python code. And it's this recursive sorting algorithm invented in the early 70s, or maybe late 70s, I don't remember exactly. And it does the following. So it sorts an array of n numbers. If the length of the array is less than or equal to 1, then it's really easy. There's nothing to do. You just return it. An array of 1 element is already sorted, and so is an array of 0 elements. Otherwise, you pick a random value stored in the array, and you partition into all of the things that are smaller than that value, so P for pivot, all of the things that are equal to that value, and all of the things that are greater than that value. And then you recursively sort all of the things that are smaller, and recursively sort all of the things that are greater. Okay? In most cases, or in the generic case, this array in the middle of things that are equal to the value should only have size 1, but it also works even if there's duplicates in the array and you pick one of those duplicates. But for our purposes now, we'll assume that The array consists of n distinct values, and actually the values are the integers 1 through n. So let's write that down. Assume this is just for our analysis so that we are able to write down the numbers that are in the array when we're doing the analysis, that A contains a permutation of 1, 2, 3, all the way up to n. Okay. So here's an example where n equals 8, and the array contains 2, 1, 8, 7, 4, 3, 6, 5, in that order. And so what does Quicksort do? Quicksort picks a random pivot, P. So let's pick P to be 7. Maybe we made a random choice and we happen to get 7. And we partition into the stuff that is smaller than 7. So that has a 2, a 1, a 3. Let's keep it in order so we don't mess it up. 2, 1, 4, 3, 6, 5, and the stuff bigger than 7, which is just 8. Okay, so there's the stuff in the first part there, there's the stuff in the third part there, and the stuff in the middle is just the number 7 itself. And then we recursively sort this part, and then we'll recursively sort this part. So we recursively sort the first part. That means we pick a random value in there out of 2, 1, 4, 3, 6, and 5. So suppose we pick the value 3 when we recurse. Then this gets split up into the stuff smaller than 3, which is 2 and 1, and the stuff bigger than 3, which is 4, 6, 5. This is the first part, this is the third part, and 3 is there in the middle. We recursively sort this part, which requires making a random choice. Let's say we pick 1 as our pivot, and then that splits it into 2 parts. And now we recurse on the stuff smaller than 1, but the stuff which is smaller than 1 is empty, so that's an array of length 0. And then we recurse on the stuff which is bigger than 1. That's an array of length 1. It contains only 2, so it returns immediately. And now we have to recurse on this side, and maybe on this side we pick, we get lucky and we pick a 5 as our pivot, and that means we have these stuff less than 5 is just 4, the stuff bigger than 5 is just 6, and when we recurse on 4, it's an array of length 1, so we return. When we recurse on 6, it's an array of length 1, so we return immediately. And so what comes out of here is 4, 5, 6. What comes out of here is 1, 2. What comes out of here is 1, 2, 3, 4, 5, 6. And then what comes out of the root is 1, 2, 3, 4, 5, 6, 7, and whatever we get when we recurse on here, but that's just an array of size 1, so it returns immediately. Okay, so that's how it works. You split into the stuff that is smaller than the pivot, sort it. The stuff that's bigger than the pivot, sort it, and you concatenate the smaller stuff, the sorted smaller stuff, the pivot, and the bigger stuff. Okay. So you've probably seen it before, and that's the algorithm. All right. So the question is, how fast is Quicksort? And well, that depends, right? That depends on the contents of the array, and it also depends on the choice of the pivot. And so I think you can see that there are maybe good choices and bad choices for pivots. For example, if you get really unlucky, then in this example, when you pick your random pivot, you'll pick the number 1. And then you'll get there's nothing smaller than 1, and there's n minus 1 things bigger than 1. And then if you're unlucky when you recurse on this side, you'll pick the number 2. Then there's nothing smaller than 2, and there's n minus 2 other things that are bigger than 2. And if you're unlucky when you recurse on that thing, you'll pick 3. And so on. Okay. Until at the very end you'll have 7 and 8, and you'll pick 7, leaving you with just 8. And that looks bad, right? Because if we look at how much work we had to do just to get from here to here, well, we picked the pivot 1, and then we compared everything to 1, and well, that means we did n minus 1 comparisons at least, because we had to compare all these n minus 1 other things to this value 1. So that took n minus 1 comparisons, and the same thing happens here, but now there's only n minus 1 things total. One of them is 2, and the other n minus 2 get compared to it. So we get n minus 2 comparisons, n minus 3, and so on, right down till the very end where we do 1 comparison. And if you add all that up, the total number of comparisons is 1 plus 2 plus 3 plus 4, all the way up to n minus 1, and you get n times n minus 1 over 2. Okay. So n squared minus n over 2. You might recognize this formula as n choose 2. That's exactly correct, because in this example, every pair of elements gets compared to each other. So each of the n choose 2 pairs of values would get compared to each other if you got unlucky like this. And then maybe in the best case, you could guess that actually, if picking the smallest thing is really bad, well, by symmetry, picking the biggest thing must be really bad, and so maybe the best thing is to always pick in the middle. And if you do that, then you get some recursion tree that looks like this, right? You have something like n over 2 in the middle, maybe there's a floor or a ceiling, and then n over 4 here, and 3n over 4 here, and you get something that looks like the merge sort recurrence, which solves to n log n. But that's the worst case and the best case. Each of these things is somehow really unlikely to happen, because we're always picking a random pivot here. So it's unlikely that we'd always pick the smallest one, but it's also unlikely that we would always pick the one that's right in the middle. So we have to do better than just these heuristics. Okay, so let's define our way. Let's avoid doing any work for as long as possible. So let's just define our way out of this. So we're working on this assumption that the array A contains a permutation of 1 through n. Let me write A like this. And let's say, well, first let me just clarify one thing. So this is Python, really simple Python code to implement Quicksort. It's not bad. I mean, you can implement this, it'll work fine, and it'll run fairly fast. But you notice that there's a little bit of redundancy, maybe. This line of code here goes through the entire array A and compares everything to X in order to extract the stuff, to P, in order to extract the stuff that is smaller than P. And then this line here goes through the whole array A and compares everything to P in order to extract the stuff which is larger than P. I think you could imagine that you don't need to go through the array A twice. Right? If you're willing to write a couple more lines of code, you can go through the array A once, and each time you compare something to P, you know if it's less than or if it's greater than P, and you put it in the appropriate place. So really, this is simple Python code, but if you do it more carefully, then you can see that you can do this using n-1 comparisons. Okay? And really this is just everything gets compared to P. You don't need to compare P to itself because you picked it already. You have to compare the other n-1 things. Okay, just so we can be a little bit clear. So let's say for each, let's take 1 less than or equal to x, less than y, less than or equal to n. Let I x, y, so this is going to be an indicator random variable, so it's going to have values 1 or 0, and it will be 1 if x is compared to y, and it's 0 otherwise. Okay. All right. So let's take a look at that. So what does that mean in our example here? Well, in our example, we might ask, is let's take I 1, 7. Okay. So it says for each choice of x less than y, we have such an indicator random variable that tells us whether those two things were compared during the execution of the algorithm. And during the execution of the algorithm, were 1 and 7 compared? Yes, they were, because in the first round, we picked 7 as the pivot, and then we compared everything to 7, including 1. Okay. So 1 and 7 were compared. So in this case, this indicator variable is equal to 1. We could ask about the indicator variable 2, 8. So was 2 compared to 8 during the execution of this algorithm? Well, let's see. In the first round, we picked 7. Everything smaller than 7 went off to the left here and became part of one subproblem. So that is 2. And that includes 2. And 8, which is bigger than 7, went off to the right here and became part of a different recursive subproblem. And we recursed on this side and completely sorted it. But while we were doing that, 8 was not involved. So there's no way 2 got compared to 8 when we were recursing on this side. And similarly, when we recursed on this side, which was a trivial recursion, 2 was not involved in this subproblem, so those two things were never compared. And so 2 was never compared to 8 during the execution of that, so that indicator variable is 0. Okay. All right. And we do one more example. Maybe we could do I 1, 4. So was 1 ever compared to 4? Well, in the first round, 7 was compared to everything, so that's not 1 or 4. And 1 and 4 went off to the left here on the same side. So maybe they were compared, I don't know yet. In the second round, in the recursive call on this side, 3 was compared to everything. Well, that's neither 1 nor 4. But when we did that, we split into the stuff less than 3, which includes 1, and the stuff bigger than 3, which includes 4. And then after that, we recursed on each side independently. So 3, the fact that we chose 3 first means that we would never compare 1 and 4. So this is important. This is the critical thing. So it's important to understand this. So 1 and 4 are never compared during this execution of the algorithm. All right. So write in the comments if you want me to do this indicator variable for a different, another pair of numbers, and I will, because it's important. But for now, let's keep plugging away. So we assume A contains a permutation of 1 to n. We define this indicator variable ixy, which tells us if x and y were compared. And so if I say let x equal the number of comparisons, done by Quicksort, then x is just going to be equal to, well, we have to sum over all the pairs x and y in the set 1 through n, where x is less than y. So that has a sum with x running from 1 up to n. And inside of that, for each of those values of x, we have y running from x plus 1 up to n. And actually that means we only have to run x up to n minus 1 of ixy. Okay. So this tells us the number of comparisons. We just add for every pair of variables or every pair of values whether or not they were compared. Okay, please do it for another pair. Good. So let's check the pair 4, 5. Were 4 and 5 ever compared during the execution of this algorithm? Okay. So we looked at, first we did 7. That split into these two parts. 4 and 5 went into the same part. Then we did, in that part, we picked 3. That split into these two parts. 4 and 5 went into the same part. And in that part, we picked 5. And when we picked 5 in this part, 5 gets compared to everything, including 4. Okay. That's how we ended up putting 4 on this side of 5 and 6 on this side of 5, because they were compared. In particular, 4 was compared with 5. So we get a 1 there. All right. And if you think about this for a little while, what you'll realize is at each stage, like when we did, for instance, 1, 4, when we looked at 1, 4, so we had 1 and 4. Now the array is not sorted yet, but let's just write down the numbers in the order in which they occur. So look what happened here. First we picked 7. So we got one part that has all of the things smaller than 7. In particular, it still has 1 and 4. And then we picked 3. And that broke that thing into 2 parts, and those 2 parts split up 1 and 4. So 1 and 4 were never compared. But if we look at 4 and 5, for example, which is what we did here, well, the same thing happens. We picked 7. 4 and 5 were both on the same side. Then we picked 3. 4 and 5 were both on the same side. And then finally, we picked 5. And that caused us to compare 4 and 5 with each other. Okay? I mean, it caused us to compare 5 with everything, including 4. So if you put on your blinders for a second, in one case, the picture looked like this. When we were interested in 1 and 4, some stuff happened. That stuff was we picked 7, and maybe other stuff happened, it doesn't matter, but at some point we picked something in the set 1, 2, 3, 4, and it just so happened that the thing we picked was 3, so 1 and 4 were never compared. On the other hand, if we do the same experiment with our blinders on, only looking at 4 and 5, some stuff happened. That stuff was we picked 7, then we picked 3, but that still didn't split them up, and then finally we picked 5, and that means these two got compared. So the picture in general is going to look like there's x plus 1, x plus 2, x plus 3, all the way up to y. And there's stuff that's smaller than x, and there's stuff that's bigger than y. And the algorithm runs for a while, picking pivots. So for a while, they're either smaller than x or bigger than y. And each time that happens, we still don't know whether x and y are going to get compared. And the first time we know, or what determines whether x and y get compared, are the first element that we pick from this set. If I pick x, then everything in this set will get compared to x, including y. If I pick y, then everything in this set, including x, will get compared to y. And if I pick something in the middle, in between those two, then x and y will never get compared, because x and y will get compared to this thing in the middle. X will go to one side, and y will go to the other side. Okay? Is that clear? So really, what determines if two things get compared is you look at all of the numbers in between them. So x and y and everything in between. At some point, the algorithm selects a first pivot in that set. And if it's in between x and y, strictly in between them, then x and y will never get compared. They'll go off onto different sides. But if it's x or if it's y, then x and y will get compared. So how many elements are in this set here? There is, well, y minus x plus 1, right? So that's the number of elements in this range is y minus x plus 1. You can check that, right? For 4 and 5, how many elements are in there? There's 2 elements in that set. That's 5 minus 4 plus 1. For 1 and 4, how many elements are in that set? That's 4 minus 1 plus 1 is 4. All right. So now we chug away here. So this is the number of comparisons performed. And we can write it as the sum of these indicator random variables, which means, of course, that the expected number of comparisons is the expected value of that sum. And as always, when we have the expected value of a sum, and in fact, the reason we did this was to break things down and make them as simple as possible. We'll take the sum of the expected values, so using linearity of expectation. So we get the double sum. And we get the expected value of I xy. X is still running from 1 to n minus 1. Y is still running from x plus 1 to n. So now we just need the expected value of ixy. And remember, indicator random variables, they have a very simple formula for their expected value. It's just the probability that they're equal to 1. So this is same double sum, the probability that ixy is equal to 1. And we've just been looking at this now, this probability that ixy is equal to 1. So if we think about this algorithm, it runs for a while until the first time that it picks a pivot inside this set. So right up until that point, this set is part of the same subproblem. Right? So it's always part of the same subproblem. It's picking pivots. They're not landing in between x and y, or not equal to x and y, until the first time the algorithm does finally pick a pivot in that set. Okay. And when it does, well, the algorithm chose a random pivot in the subproblem, and the pivot happened to land inside this set. Okay. So there's a conditional probability thing we can do here, but it's kind of boring, and the answer won't surprise you. But if I take a random element from some set and I condition on the element being in a particular subset of that, then each of the things in that subset is equally likely. So it means the probability that the first thing I pick, the first pivot chosen from here is x, well, that's going to be 1 over the size of this set. The probability that it's x plus 1 is 1 over the size of this set. Probability that it's x plus 2 is 1 over the size of this set, and so on. So the probability that ixy equals 1 is equal to the probability that the first pivot among x up to y is x or y. And that is just, well, x or y, that's 2 elements, out of a set of size y minus x plus 1. All right, so now we know this value, and we can finish up. So now we're looking at the sum, x running from 1 to n minus 1, y running from x plus 1 up to n of 2 over y minus x plus 1. Okay. Good. So we have a double sum, and inside that double sum, the factor 2 appears in every term. So let's just take it out front. Okay. And now, if I look at this thing. So let's do this longhand so you see what's happening. So fix some value of x and start looking at this inner sum. So the inner sum starts at with y equal to x plus 1. Okay, so this starts with y equal to x plus 1. So that means y minus x is 1, plus 1 is 2. So the first term in there is going to be a half. Next, next time through, y is equal to x plus 2. When I put that in here, this thing becomes a third. Next time through, this becomes a quarter. And so on, all the way up to, well, it is the difference between x plus 1 and n, so this goes all the way up to n minus x. So 1 over n minus x. Okay, good. So this looks kind of familiar. It's not exactly what we have here, but I should put the dots in between these two things. It's not exactly the harmonic number, it's just missing somehow one term here. There's a missing 1 in front, and there's a missing, well, it's not missing, it's the n minus x harmonic number minus 1. So let's make lives easy for us. We want a clean answer. So instead of running this all the way up to n minus x, let's run it even further. Let's let it go all the way to n. And when I do that, then this thing here is the nth harmonic number minus 1, because it's missing the first term. So we get 2 times the sum x equals 1 to n minus 1 of h of n minus 1. And, well, we can do lots of things. This thing here is, if we want to be really simple, this thing here is less than or equal to h of n. Oh no, let's leave that for now. Well, x goes from 1 to n minus 1, so in fact this thing is equal to, so we have n minus 1 terms, they're all the same, they're all h of n minus 1, so we get 2 n minus 1 h of n minus 1. We saw that h of n is less than or equal to the natural logarithm of n plus 1. So this is 2 less than 2n minus 1, the natural logarithm of n. Right. Natural logarithm of n plus 1 minus 1 is just the natural logarithm of n. And so that is less than or equal to 2n ln n, in this case minus 2 ln n. Okay. So the expected number of comparisons done by Quicksort is not more than 2 times the natural, 2n times the natural logarithm of n. So let's write that down. The expected number of comparisons done by Quicksort when sorting an array of n distinct values is at most 2n natural logarithm of n. Okay. And if you want, so I dropped again another lower order term here, but I only want this at most, and this is a nice clean formula, the easy thing to remember, and it's the most important thing. There, in fact, we could be more careful here. We dropped a few different things and get, 2n ln n minus something, but that something is not going to be more than a constant times n. Okay, good. So we get this weird result, simple algorithm, easy to implement, and it's, if we look specifically at the number of comparisons, we get this strange thing that has the natural logarithm of n. So inside the natural logarithm of n, that means Euler's constant is in there. So that's already looks a little bit weird. And where does this come from, this natural logarithm? Well, it comes because we're approximating the harmonic number by the natural logarithm. So it's a decent approximation. I mean, it's very close to the truth. In fact, it captures the most important term in the number of comparisons, which is 2n natural logarithm of n. All right. So that's about Quicksort. Let's look at a related thing. Let's look at a random binary search tree. So what is a random binary search tree? Well, the way you get a random binary search tree is you start with a random permutation. So let's take a random permutation of 1 through n. So we have the integers 1 through n. They're permuted in some random order. And we imagine we start with an empty binary search tree, and we insert the things in the order they appear in the permutation. Okay. So let's say that our permutation, it's going to be a permutation, let's take n equals 8. And we look at the first element in the permutation, and we add it into an empty binary search tree. So let's suppose that the first element is 7. There's more coming, but I only need to know the first one for now. So that means we make a binary search tree that has one node, and it has the value 7 in it. Now, we look at the next thing in our random permutation. And let's pick at random something from 1 through 8, not including 7. And so let's suppose that that's 3. So we insert 3 into this binary search tree. 3 is smaller than 7, so it should go into the left subtree, like so. And now we look at the next thing in our random permutation. And maybe the next thing in our random permutation is 1. We insert that into this binary search tree. We get 7, 3, and 1 goes here. Next thing in our random permutation, maybe it's 8. So 8 is bigger than 7, so it goes there. Let's say that the next thing that we see is, let's say 5. 5 is smaller than 7, but bigger than 3, so it should go there. And I don't know, maybe next we see 4. So smaller than 7, bigger than 3, smaller than 5, so it goes there. Maybe the next thing we see is a 2. So that goes there. And then finally the next thing we see, I think there's only one thing left. 3, 4, 5, 6. Smaller than 7, bigger than 3, bigger than 5. 6 goes there. So there's a random permutation of the integers 1 through 8. And if I insert them into a binary search tree in that order, this is the binary search tree I get. Someone asked, where does the -2 ln n come from? That was because we had a formula that had a 2n minus 1 ln n. Okay. So 2n ln n, and then there was this minus 1 here. So that's a -2 ln n. And where did n minus 1 come from? That came because x was going from 1 up to n minus 1 only. All right. So that's the definition of a random binary search tree. Does it look familiar? Does it sound familiar? Even if you haven't taken COMP2804 or you're not taking it with me, does that definition of a random binary search tree sound familiar? Think about it for a few minutes. And if you've been paying attention, you might think that, I mean, I said I was picking random numbers here, but you might suspect that. You might be suspicious about whether that was true or not. So the way that I defined this permutation was I picked the first thing to be any one of the 8 possible numbers, and I picked one at random, let's say. Yeah. And so I happened to pick 7 as the first thing. So I had 8 options, and I happened to pick 7. That means 7 becomes the root of my binary search tree. Now, think about that, and think about what's going to happen during the rest of the time that I build this binary search tree. Well, this thing is always going to be at the root. So I picked it first, so it's always going to be at the root, which means that everything else that I insert later on is going to have to pass through the root, and each of those things that I insert later on, we're going to have to determine whether it should go left at the root or whether it should go right at the root. And how do we determine whether it goes left or right at the root? We compare it to the value at the root. Okay? So that first element that I pick is going to be compared to everything. In fact, there's going to be n-1 comparisons involving this and all the other elements. All the other n-1 things are going to have to go through it. And eventually, each one of them will go through that root and be compared to it. If you think about Quicksort, what did it do? It had all the options, 8 options to choose from, and it randomly chose one that happened to be 7. And then Quicksort said, okay, well now I'm going to make a couple of bags here. The stuff smaller than 7 and the stuff bigger than 7. So Quicksort then, after it picks 7, it immediately compares 7 to everything else and decides whether they're going to go over here on the left, or so before in the array, or over here on the right after in the array. So Quicksort had 8 things to choose from, and it chose one and compared everything to it. The random binary search tree had 8 things to choose from. It chose one, and eventually it will compare everything to that thing that it chose. Okay. Now, Quicksort then recurses on this side. I didn't do that when I was picking these things necessarily. So the second element here could be any element from the whole set except for 7. But the things that are smaller than 7 are going to go over here, and the things that are bigger than 7 are going to end up over here. So in particular, there's going to be a first thing that I pick that is smaller than 7. In this case, it was the next thing, but I might have picked 8 before this. And that first thing that I pick that's smaller than 7 is going to become the root of this. And everything else that's smaller than 7 will have to be compared to this thing. In Quicksort, when I recurse on the left, I pick something randomly from this set, and then everything is going to get compared to it. So in Quicksort, I picked a 3 from this set, and then that split things up into 2 bags, 1, 2, and 4, 5, 6. And the same thing is going to happen here, right? So after I pick 3, there's still all of these other things to come through here, and everything smaller than 7 is going to go this way, and it's all going to get compared to 3, so that's all these elements, 1, 2, 4, 5, 6. They eventually will, each one of those gets compared to 3, and it'll live in the subtree rooted at 3. And you can check that, you know, this happens all over the place. Okay. So, so Quicksort, the Quicksort recursion tree, if you label it with, you know, each node of the recursion tree with the choice of pivot at that node, what you actually get is a random binary search tree. if you imagine you ran Quicksort and you built a random binary search tree, then all of the comparisons that get done are the same comparisons, but they happen in a different order. Quicksort gets them all out of the way up front, so as soon as you pick a pivot, you compare everything to it. In a random binary search tree, when you pick this next element to be the root of some subtree, eventually everything that's in that range will get compared to it. It doesn't happen immediately, but you could imagine doing it immediately, and then you would just get exactly Quicksort. Okay. So, really close relation between Quicksort and random binary search trees. All right. Now, we saw that Quicksort does a number of comparisons, which is 2n ln n. Somehow the harmonic number comes into play. And we can kind of imagine 2n ln n. That's a little bit like, if you think of one particular element in Quicksort, well, there's n elements that you're sorting in total, so on average, and this is a very rough intuition, one of the elements is involved in at most 2 ln n comparisons. Right? If I pick a particular element and say, how many comparisons were you involved in? Well, it feels like the expected number should be 2 ln n. So let's try and sort of formalize that a little bit and think about what it means in terms of these random binary search trees. And let's do it with an example. So let's think about this random binary search tree that we constructed here. And imagine that we go searching in this random binary search tree. Imagine we go searching for 4.5. So when we search for 4.5, we start at the root. Uh, 4.5 is smaller than 7, so we go left. It's bigger than 3, so we go right. It's smaller than 5, so we go left. And then it's bigger than 4, so we go right, and we fall out of the tree. So these are the nodes that we see when we go searching for 4.5. 7, 3, 5, and 4. So let's think about whether there's a way to describe those. So at some of those nodes, we went left. At some other nodes, we went right. From 7, we went left. From 5, we went left. From 3, we went right. From 4, we went right. Now, why did we go left at 7? Well, because 4.5 is smaller than 7. Why did we go left at 5? Same reason. 4.5 is smaller than 5. And similarly, 4.5 is bigger than 3 and 4, so that's why we went right at those nodes. So maybe it makes sense then to take this permutation just for the sake of studying 4.5 and how we got these nodes on the search path. Let's split it into 2 permutations, the stuff which is smaller than 4.5 and the stuff which is bigger. So the smaller stuff is 3, 1, 5, 4, 2. I forgot to write in the last number. 6. 3, 1, 5, 4, 2. And the stuff which is bigger, oops, not 5. 3, 1, 4, 2. And the stuff that's bigger than 4.5 was 7, 8, 5, and 6. So that's, things are appearing in the same order, but I've just split it into stuff smaller than and the stuff bigger than. Now, let's look at what's happening here. Imagine there's the number 4.5 on the real number line. And, before I do anything, before I do any comparisons with 4.5, I don't know where any of the stuff in the tree lies in relation to 4.5. Okay. So let's look at let's look at one of these things. Let's look at this one, 3142. Okay, so right now 4.5 is this big thing. I know nothing about it, so in some sense, I don't know where it is anywhere on the number line. And then we look at 3. 3 comes along, and I know that 4.5, I compare it and I see that 4.5 is bigger than 3. So that point, that's sort of what I know about 4.5. And then 1 comes along, and 1 doesn't tell me anything new about 4.5, right? So if you look in the tree, what happened is 3 was inserted first, 4.5 went to the right there, and then 1 came along and was inserted, and 4.5 didn't need to get compared to it because it already went to the right at 3. Okay. So 3 was interesting, but 1 was not interesting. Then 4 comes along. That's 4. And 4.5 actually gets compared to 4. And that's because somehow 4 tells us more than, tells us even more than 3 did. So 4 is interesting. And then later on in the permutation, 2 comes along, which is over here. Doesn't tell us anything really new. All right. So these are the things that 4.5 gets compared to in this stuff, among the stuff that is smaller than 4.5. All right, let's do the same thing now for the bigger stuff. Well, 7 comes along. So we can imagine working in this direction now. So we know nothing, let's say, about what's bigger than 4.5. Then 7 comes along. And that tells us that. Then 8 comes along, which tells us nothing new. So 7 was useful, but 8 didn't tell us anything. And then 5 comes along. Which tells us something new. And then finally 6 comes along, which doesn't tell us anything because it's bigger than 5. So in this array, the stuff that gets compared to 4.5 in this subpermutation is 3 and 4, and in this one it's 7 and 5. So think about this one for a bit. Basically, as we construct this binary search tree, what was happening is that before we started, there was a giant interval, nothing was in the binary search tree. First thing we did was insert 7. And 7, before we insert it, it's in the same interval as 4.5. 7 goes there. Then 3 comes along. And really the binary search tree has 2 intervals, the stuff bigger than 7 at this point and the stuff smaller than 7. And 3 is in the same interval as 4.5. But now there's a real interval that contains 4.5. It's between 3 and 7. And other stuff that comes along, like 1, isn't in that interval. 8 is not in that interval. So it doesn't follow the same search path that 4.5 eventually will. Then 5 comes along, and it is in this interval between 3 and 7, the same one that contains 4.5. Okay. So now this is the important interval 3, 5. Then 4 comes along. It's also in that interval. So now the important interval is 4, 5. And everything else. 2 comes along, it's not in that interval, so it won't follow the same search path that 4.5 eventually will. And then 6 comes along, it's also not in that interval, so it won't follow the same search path. Okay, so here comes the punchline. Look at these guys here. This is a short permutation. It's a permutation of 4 distinct values. What's special about 3 and 4 in this permutation? No guesses? What if I wanted to compute in this list here, this array, 3, 1, 4, 2, what if I wanted to compute the maximum value? Okay, so one guess is 4 is halfway between 7, and 1 and 3 is halfway between 5 and 1. That is a reasonable guess, but it's not what I'm hoping for. So if I want to compute the maximum value in this sequence of numbers, what happens? Here's an algorithm for computing it. Okay, so we can run the algorithm. First time through the loop, the maximum value is minus infinity. 3 is bigger than minus infinity, so this is the maximum value so far. So first time through the loop, that's the value of m. Second time through the loop, we see this value, which is not bigger than m, so nothing happens. Third time through the loop, we see this value, 4, which is bigger than m, so this becomes the maximum value. And the last time through the loop, we see 2, which is not bigger than m, so nothing happens. So if I ran this algorithm on this sequence of numbers, m gets updated here and here. Okay. And why is that? Is that and that just happens to be the two numbers on the path to 4.5. Is that a coincidence? No, it's not a coincidence, because if you just think of this picture here, you initially start out with the empty thing, 4.5, with the empty search tree. So 4.5, if I search for it in that tree, nothing will happen. But then things start falling in. Things start getting added, like 7 gets added. And then if I search for 4.5, well, it's going to be over here in this interval. And then 3 gets added. So if I search for 4.5, it's going to be between 3 and 7. And so in particular, when 3 got added, the interval that contained 4.5 got smaller. And the same thing when 7 got added. But why did that happen when 3 got added? Well, that happened because 3 was the biggest number that is smaller than 4.5 that we've seen so far. In fact, you can imagine before 3 was added, the interval that contained 4.5 was minus infinity 7, and then 3 came along, and it replaced minus infinity. And then later 1 came along, but that doesn't do anything. It doesn't make this interval any smaller. But then 4 comes along, and it replaces 3. So it's not a coincidence that if I look at all of the things in this sequence which are smaller than what I'm looking for, that each time I see one that's larger than any of the previous ones, that is something that will get compared to 4.5. And the same thing happens here, except now instead of the largest having to see something larger every time, I just have to see something smaller every time. And for the same reason, right? In the empty tree, 4.5 is contained in this infinite interval, minus infinity to plus infinity. Each time you see something bigger than 4.5, that could make the interval smaller if that thing that you see is smaller than all of the other things bigger than 4.5. So the point then is, well, if I do this splitting, so we call this, pi less than x, and we call this pi bigger than x, that's this thing here, then the number of the number of nodes on the path that I see that are less than x is exactly the same as the number of times this line would execute if I ran it on this permutation. Now this permutation is just the list of all things that were smaller than x. In this case, x is 4.5. And so it's a random permutation, but then you pull out only the things that are smaller than a particular value. So that still means that among all of the things that are smaller than that value, this is still a random permutation. So in this case, there's 4 factorial such permutations. Each one is equally likely. So you can work out you can just do the counting on the number of these permutations and the probability of each one, and you'll see that they're equally likely. Okay? So all that to say that there's another sort of theorem here. If we search for x plus a half for any x in, I think you can go 0 up to n, in a random binary search tree, then the expected length of the search path is h of x plus h of n minus x. So if I pick a number that's not in the tree, which is why I say x plus a half, like 4 plus a half, then the expected number of things that I will see which are smaller than x is, well, there's going to be, there are x things that are smaller than x plus a half, and the expected number of those things that I will see is the harmonic number of those things, because they're in exact correspondence to executions of this line if I were to run on this permutation. And the number of things which is larger than x plus a half is n minus x, and so that's the expected number of those things that I will see. Okay. Okay, so so there you go. Now you know actually exactly the expected length of a search path in a random binary search tree if you search for something which is not in the tree. Okay, so that's why this specifies x plus a half, and the tree itself stores the integers 1 through n. And if you search for something that is in the tree, well, it's not going to be more than if you search for something that's the same thing that's not in the tree, right? So here, if I, instead of searching for 4.5, if I wanted to search for 4, well, that search would just stop one step sooner. If I wanted to search for 3, for example, the search would stop here, but if I search for 3.5, the search actually would end up over here. So it's always harder to search for something that's not in the tree than something that is in the tree. So this gives an upper bound for anything that is in the tree. And you can analyze Quicksort the same way if you like now, because all you have to do is sum up for each x its depth in this tree, and this tells you that the expected depth of, this gives you an upper bound on the expected depth of x. And so that's where the 2 ln n is coming from, right? For each x, I'm getting an h of x, which is not more than ln of n plus 1, and I'm getting an h of n minus x, which is also not more than ln of n plus 1, and so I'm getting, that's the 2 ln n's, 2 ln n's for each element there. All right, so that's a good place to stop. And the sort of moral today is remember that Quicksort and random binary search trees, they're really the same thing, and that both of them are somehow closely related to this silly algorithm for computing the maximum in a list of numbers, or the minimum if you like. So I can take a question or two if people have some. Okay, so looks like there's no questions. Thanks for showing up today. I'm sorry that my cat was not a little more entertaining. Maybe some of you showed up just for hope of a live replay. But I'm also glad my cat didn't fall through the roof again. When can we expect to have the interactive quizzes ready for final exam prep? I have no idea because I have nothing to do with making the interactive quizzes. So the people who have been doing that are Carleton undergrad students who did it as a sort of hobby project. So it has nothing to do with me. You would have to ask them. But I mean, you know that the sources of those quizzes, they come from the old final exams, which are available on the course webpage, both mine and the other professors. So you're already able to take practice final exams if you're interested. All right. So have a good day, and I will see you on Wednesday.